Just like when the alcohol expands in a thermometer, liquids and solids expand when heated in other places. When the particles expand, it causes a decrease in the density of a substance. Hot air rises, cold water sinks. These are key forces involved in ocean and atmospheric circulation. It is also an important concept in engineering of roads and bridges. If the temperature of a substance is increased, the kinetic energy of the substance increases. If the particles are moving faster, the collisions between the particles are stronger and cause slightly larger distances between them. This increase in space between particles causes the object to expand. When we build bridges, for example, we have to account for the fact that in the summertime, temperatures will cause the bridge to expand, and in the winter, cold temperatures will cause it to contract. Over time, this expansion and contraction can do significant damage to the structure, so we put joints at certain intervals to help alleviate this stress. Different substances expand at different rates. The table in your textbook lists the thermal expansion coefficients for different materials. This is not even close to an inclusive list, even of the substances listed here. Notice that the coefficient is valid if the substance is close to 20 degrees Celsius to begin with. These values are also only appropriate for small temperature changes. Other values are available for different situations, but for our purposes, these will do nicely. The expansion of a substance depends on several things. One is what the substance actually is. This is represented as the coefficient of expansion in an equation as alpha in our linear expansion. The amount of substance that you start with will also affect the expansion, so we take into account the initial length of the object. Longer objects will expand more than shorter objects simply because there are more particles to expand. Finally, we need to know how much the temperature has changed. This temperature can be determined by either a change in Celsius or a change in Kelvin degrees. We know that the main span of the Golden Gate Bridge is 1,275 meters long at its coldest. If the temperature ranges from negative 15 degrees Celsius to 40 degrees Celsius throughout the year, how much does its length change? We know the length and we know the change in temperature. Using our equation, we just need to determine the coefficient of linear expansion. The ridge for the most part is steel, so we can use that as our substance. We end up with an expansion of 0.84 meters throughout the year. When a substance expands, it does so in all directions, so the area and the volume of the object will also expand with increasing temperature. The equation for the area of expansion is similar to the linear expansion in that it uses the same coefficient. Since the expansion occurs in 2 dimensions, we multiply that value by 2. Volume expansion gets its own coefficient, but still follows the convention of the original linear expansion equation. If you take that metal plate and cut a hole in it, the hole will also expand at the same rate. Suppose your 60-liter gas tank is full of gas. So both the tank and the gas have a temperature of 15 degrees Celsius. How much gasoline spills out if the temperature warms to 35 degrees Celsius? In this case, both the tank and the gas are expanding, so we have to take both into account. We are looking at volume in both instances, so we will use the same equation for the tank and the gas. The volume of this steel tank is 60 liters and undergoes a temperature increase of 20 degrees Celsius. This gives us a change in volume for the tank of 0.042 liters. The gas has a much higher coefficient of expansion, so we would expect more of a change in volume. In this case, our gasoline expands to 1.14 liters. We started out with a full tank, so to figure out how much gas was actually spilled, we need to find the difference in the expansions. In this case, it's 1.10 liters of gasoline. Most things expand when the temperature increases. Water is a very important exception. Between the temperatures of 0 and 4 degrees Celsius, water actually expands when the temperature decreases. What happens when you put a bottle of water in the freezer? If it's full enough, that water is going to expand and it's going to explode your bottle. Water is actually at its densest at 4 degrees Celsius. If you think about a pond in the wintertime, the water near the surface cools down to 4 degrees Celsius, and the density increases. Since it is more dense than the water below, it sinks. Eventually, the water that has risen to the top cools to 4 degrees Celsius, and so on and so forth. The pond eventually reaches a uniform temperature of 4 degrees Celsius. The top layer of water can now cool further and actually freezes. The ice acts as an insulator for the water below. So the top freezes over and the fish below can survive in the water just above freezing. Whenever a substance expands, it puts stress onto itself and/or its surroundings. This is referred to as thermal stress and can be used to explain many phenomena in the natural world. For example, water seeps into cracks in rocks. When the water freezes, it expands and causes stress on the surrounding rock. Manufacturers also use this property of matter when assembling parts. One part can be heated so it expands, allowing it to be slipped over another part. When the system cools, the two parts are joined together.